Hello and welcome to the world of NDE 4.0. My name is Johannes Vana, and today is a great day because today we will continue our excursion to the world of ultrasonics. Now, we already did a couple of videos on sizing with ultrasonics. And today we will add on to that. But today we will discuss small defects, the sizing of small defects. And with small defects, I actually mean tiny defects. Defects clearly smaller than the wavelength. Now, this video, it is quite long. And I have to show you some math to help you understand what we did. So it could be that some of you might doze off in between. But it will do three things. Number one, I will use chapter markings as always. Number two, I will tell you once you can fall asleep and once you should wake up again. And for sure, I will also do key takeaway messages. But before I get started, I have to ask you a small favor. I guess you know that YouTube uses artificial intelligence to evaluate a channel. And I guess you also know that I already did a couple of videos on AI, and you will find a link to actually the playlist of all my AI videos right here. Now, but that YouTube evaluation, that depends on the user interaction. The more interaction, the higher the rating. Therefore, please subscribe to this channel. Please click on that little bell. Please give a thumbs up to all the videos and watch all the videos. And the two most important ones, please write a lot of comments, ask all the questions you can think of, and please watch all the videos all the way from the beginning to the end. Because this is how you can support this channel, and this is how you can bring non-destructive testing and non-destructive evaluation to the world. And now, let's get started. As I already said, we already discussed the topic of sizing. And with ultrasonics, we always need two different methods for sizing. For indications which are larger than the beam diameter, we can actually do sizing by probe travel. So we take our probe, we go here, we see, we see some indication, then we move the probe, it's getting bigger and it's getting smaller again, and okay, it goes from here to here. So that's kind of the size of the indication. And the typical method for that kind of sizing is the 6 dB drop method. Now, for indications which are smaller than the beam diameter, we have to use something else. Because actually, what we do with smaller indications, we just measure the size of our beam. So it doesn't change anymore if we change the size of our indication. So we need something else. And what is typically done is we take the reflection of our indication, because the reflection of our indication changes with the size of the indication. So we take the reflection and we compare the reflection with the reflection of an artificial reflector, like a flat bottom hole. And then we can say, okay, this indication looks like a flat bottom hole with 2 millimeters of diameter. Now, those two sizing methods were discussed in detail in this video, and I will leave a link to that video right here. We also discussed sizing with DGS. Now, for large indications, we can still use probe travel, but for small indications, especially here in Europe, another method is used. A method where we do not need all those different calibration blocks. Instead, we use one diagram. One diagram actually for every single transducer type has a certain diagram. And then we go into that diagram and see, okay, this indication has a reflectivity like a disc-shaped reflector with 1.5 millimeters. Again, very similar to the DAG method, but instead of using calibration blocks, we use those diagrams. The details to the DGS or AVG method you can find in that video, or you can find the link right here. Now the question comes up, how accurate are those methods? And do we have limitations? And yes, we have certain lower limits and we have certain upper limits. And the lower limit of DAC and DGS, that really depends on the wavelength and on the sound path. So it actually doesn't really depend on the beam diameter. But if we calculate it, we can see that the upper limit is around 0.3 to 1 time the beam diameter. On the other side, the method for the big indication, the 6 dB drop method, its accurate lower limit is around 1.5 times the beam diameter. So what we have a gap between those two. So if you find an indication which is somewhere in the range of about somewhere between 0.5 and 1.5 times the beam diameter, then you should be taking a different probe with a different beam diameter, with a different frequency, with a different whatever, so that you can get an accurate reading within that gap. More details on this subject you can find on that third video, where you can find the link to that video right here. Now in this video, we will not focus on any of those topics. We will focus on the lower limit of DAC and DGS. For sure, now comes the question, how do we determine this lower limit? And does a number 1 flat bottom hole make any sense? Now, for the Europeans within us, a number 1 flat bottom hole is a flat bottom hole with about 0.4 millimeters of diameter. Now, you will find some rumors out there. Some people say the lower limit is the wavelength, which for a 2 megahertz probe in steel would be somewhere around the 3 millimeter. Some say it's a quarter of the wavelength, which would make the lower limit for 2 megahertz in steel to about 0.7 millimeters. But you will, if you speak with inspectors, they will tell you that they have detected and sized smaller defects. So what's really the lower limit? Now, to determine it, we could do experiments or we could do simulations. Now, experiments. Have you ever tried to produce a number 1 flat bottom hole? Yeah, that will be challenging. And now instead of going to 0.4, let's say we want to do a flat bottom hole with 0.1 millimeter. That will be a real challenge. That's challenge number 1. That's a technical challenge. But actually, and that's something we will see within this video, that actually a small flat bottom hole isn't really a good model for a real defect. So we actually cannot take a flat bottom hole for an experiment for a small reflector. We would have to use real indications. But on the other side, real indication we cannot really bring into the components. And if they are already in the component, then we would have to measure them first. But do we know that the measurement is accurate? So experiments are at least very complicated, if not even impossible. But also for simulations, we will come to the conclusion in this video that the usual tools we are used to use, that they are not good enough. So what do we do? Okay, let's look a little bit into the situation we have. We have our real defect. Here you can see a microscopic image of a real defect. And what we do to make a sizing simpler, based on the reflectivity, we do one step of abstraction. We go from a real defect to a disc-shaped reflector. So that is something which is flat and round. So it's flat to the sound hitting it, and it's round in terms of the beam diameter, like you can see it here on the top view and the side view of that reflector. Now, we cannot really manufacture disc-shaped reflectors, so we go one step further, because we can produce actually flat bottom holes. Now, but here comes the problem. We have an abstraction chain. We have a simplification from the real defect to the disc-shaped reflector. And we have another abstraction or another simplification from a disc-shaped reflector to a flat bottom hole. So from that abstraction chain point of view, we already know that disc-shaped reflectors are better in terms of being close to a real defect than a flat bottom hole. So what we will do, we will look into both of them. We will look into the disc-shaped reflector, and we will also look into the flat bottom hole, one after the other. And we will see how long do they work, what's their lower limit, and is there some way that we can extend it? Now, one point to, why for a small indication, or why for a big indication, do we have that flat bottom hole is actually a good model, but for a small indication, it actually is not. And the reason for that is really the so-called Kirchhoff approximation. Now, what's the Kirchhoff approximation? So we have our UT beam. Within that UT beam, we have our reflector. And then Kirchhoff tells us we only take into account the illuminated or the front side of the reflector. And we forget about the rear or the shadow side of the reflector. So as long as the Kirchhoff approximation is true, it doesn't matter whether we have a bore or we don't have a bore. Now what we can do, as long as Kirchhoff is true, we can say, okay, our echo amplitude is proportional to our reflector, proportional to the illuminated area. And the basis, or this is actually the basis for the so-called inverse square law, or also this equation, which is the basis for the DGS-Diagram information in the far field. And as you can see, that our gain is actually proportional to the size of our reflector squared divided by the square of our sound path. And we know that Kirchhoff is true for indication larger than wavelength. And within this video, we will see why this is the case. But now we know that it's only true for indication larger than wavelength. So the question comes up, okay, what's the case smaller? And can we extend DAC and DGS for smaller indications? We already discussed experiments. They are nearly impossible. And actually tools like SIVA, they also assume the Kirchhoff, or they also take into account the Kirchhoff approximation. So they don't help. So we had to do something different. And we chose to actually use the so-called EFIT method, Elastodynamic Finite Integration Technique. Now that is based on a work which was done by Karl-Jörg Langenberg, René Marklein, and Klaus Meyer. And we took their book, and we had a great intern, Alexander Seber, and Alexander, he implemented EFIT for our industrial application. And here you can find that paper we wrote on the basis of his master thesis. And you can find a link to that paper right here. Now I have to warn you, we will discuss a couple of slides which are quite heavy on math. So if you want to doze off, now is the time. Now, we implemented EFIT. And for EFIT, what we have to do is we have to do a spatial discretization of our three-dimensional space. We divide our space into small volumetric elements, small voxels. And it's not just one grid, it's actually a double staggered grid. And on this double staggered grid, we solve those equations. And every volumetric element has to be tiny, really, really tiny. Now the benefit of doing this is we are taking all the physics with us. We don't do any Kirchhoff. No, we take all the physics with us. It's a lot of computing we have to do for that. But on the other side, we will get as close to the real situation as we can. Okay, now you can slowly wake up again. What we did is we first tried to do some simulations to give ourselves a picture of what can we actually see. So instead of simulating a large component, we only focus on the interaction of our wave with our indication. So a very small volumetric element, or a very small volume, which we divided into all our small voxels. Then we had a plane wave, which we coupled into our component. That plane wave was then traveling through our component. We had some indication in our component, so we got a reflection. But for sure, our incoming plane wave was also traveling past our indication. And then on the outer section, we actually have a dummy grid and a absorbing layer, so that if we get any ultrasonic waves going actually to the edge, that we don't get reflection all over our result. And this is one of the snapshots we got out of this experiment or out of this simulation. What you can see is actually what we did is we coupled our beam somewhere over here. Then our beam was traveling over here. Then here we have the interaction with that indication. And now our beam is already over here. So this is our incoming wave, which has already passed the indication. But on the other side, we have here our reflected wave. Moreover, we have some induced shear waves, and we have some Rayleigh head waves. Now, this does not only work, or what we did here, this is a disc-shaped reflector. We didn't only do disc-shaped reflectors, we also did flat bottom holes. And now, the situation we had here, we simulated here a pretty big indication. So actually, Kirchhoff approximation is true. But still, we can already see some difference between a flat bottom hole and a disc-shaped reflector. So far, so good. So now, we discussed that abstraction chain before. We said, okay, we have the real defect, and we have a simplified model, which is our disc-shaped reflector. And then we do a second abstraction chain, and going towards a flat bottom hole. But now, for the start, let's just have a look onto disc-shaped reflectors. Now, what you can see here, this is a diagram where we can see on the one axis, we can see our gain. And on the other side, we can see our indication size, our diameter of our disc-shaped reflector. And what you can see is actually, we didn't choose a linear display here. You can see that actually this scale here, up here, is logarithmic. So down here it's 0.1. Here we have 1, and up here we already have 10. And that is why down here you can see we have here this quadratic dependency. And if we do this logarithmic display, then actually this quadratic dependency becomes here a straight line. So this is actually the dependency between our gain and our indication size. Now, what we already know, we know that for big indication, actually DGS is a good method, and we know that our inverse square law, and we know that that equation should be true. Meaning, all the simulations we did should be on that axis, at least all the large indications. Now, once we come to small indications, we have to see, do they stay on the line? Are they going to be bigger or smaller? And as you can clearly see, we do not get as much reflection from those small indications than we think we would be getting. Now, if we just look onto the small ones, we see that they are also on a straight line. But this time, this line is not quadratic, but this is a cubic, so a df to the power of 3 line. And actually those two, where they intersect, that is exactly a quarter of the wavelength. So what is happening? Everything which is bigger than half of our wavelength, this is where we have geometrical scattering. This is what we all know. Smaller than 1/6 of the wavelength, that's called Rayleigh scattering. Now, some of you might be saying, but doesn't Rayleigh scattering have something proportional to the power of 4? Yes. It is wavelength to the power of 4. But it is size of the reflector to the power of 3. Just a small excursion. Okay, so we have Rayleigh, we have geometrical, and in between we have some resonance effects, and we have that point where the two intersect, and that's a quarter of the wavelength. Now, we would like to having this theory and this theory as one thing, but we would like to have one theory which describes actually all what we can see here. And actually the math for that is not that complicated. We take the term which we already have and we extend it by the second term. And that's this black line which we can see here. And we can see that this term now is a pretty good description of our truth, of the situation of our real indications. So now we have a tool to describe how a real indication would reflect, even if it's getting tiny. But on the other side, we can now also see, okay, if we use DGS, if we use disc-shaped reflectors for sizing of small defects, how much undersizing would we get? It's getting serious. If we're going down to 0.1 millimeter indication size, we would have an undersizing of about 17 dB. Don't use it. Everything below a quarter of the wavelength, don't use it. Now, here comes the question, why is that the way it is? And now we are coming back to the Kirchhoff approximation we discussed in the beginning and seeing why Kirchhoff is true for large indications and not true for small ones. So let's have first a look onto large indications. In this case, this is a 3 millimeter big disc-shaped reflector. And here on the left side, you can see here in blue, this is the front of our indication. And the red dots, that is the back of our indication. And what we will see in a second is that once the wave comes onto our indication, then the front is excited first. And nothing happens on the back. And after a while, we see that some wave is coming from the edges of that indication, traveling towards the center. And now it's doing it on the front and the rear. Okay, so first we see an excitation of the front. And now we are seeing this wave coming from the edges of our indication to the center and back. Once more. Just the front, and now we see an excitation of both the front and the back going from the edges to the middle. So this is why Kirchhoff is true, because that first reflection, that first excitation, is really what is causing our reflection. And that is just the front. We just excite the front. But now let's go to a way smaller one. This time a 0.1 millimeter big indication. And now what we can see is that once we have our wave coming in, then we actually see an excitation of both our front and our back at the same time. here you can see this once more on some images. The big one, we only see something on the front, nothing on the back, and then we see this wave traveling from the edges to the middle and back. On a small one, we only see an excitation of the front and the back at the same time. So it's like that wave coming and grabbing that indication and shaking it in total. So for a small indication, we have to take into account the back to actually calculate our reflection. And this is why Kirchhoff is not true anymore. Now, on this step one, on the disc-shaped reflectors, a short summary. So we have seen that DGS diagrams are true down to 1/4 of the wavelength. Don't use them for anything smaller. However, we can extend DGS using that formula I showed you a couple of slides before, and I will show it more in detail a couple of slides later. Just what we have to do, we have to change from this cubic, or from the quadratic to a cubic dependency on our indication size. And we have seen that big indication, that we only excite the front of our indication, and that only the front is therefore giving us a signal. But on the small ones, we are grabbing that indication with our wave, exciting all of that indication, and therefore all of that indication is giving us a reflection. And that's why we move from this quadratic to the cubic dependency. Now that was step one. Now let's do abstraction step number 2, going from a disc-shaped reflector to a flat bottom hole. Now we already know by now that our Kirchhoff approximation is not true for anything smaller than 1/4 of the wavelength. So it would be surprising if flat bottom hole would be a good method, because we already know that the disc-shaped reflector is something with a couple of question marks. But let's have a look into it. Let's see how bad is the situation. So we know that for real indication that the black line is our truth. Now let's do the simulation of the flat bottom holes. And that's those dots. So again, we have undersizing. Something down to about 13 dB of undersizing. So the most important, don't ever size anything with flat bottom holes smaller than 1/4 of the wavelength. Don't do it, never ever. And if somebody asks you to do it, then send him this video, send him my name, and I will discuss with them. Because it's just ridiculous. And even if you could, then look into the quality of those small flat bottom holes. Different story. But don't do it, never, ever. 1/4 of the wavelength, nothing smaller. Now, we already discussed that with DGS, we have the potential that we can go smaller. We can do a correction. And what you can see here, this is a traditional or conventional DGS diagram, which uses for the calculation of the far field the equation we see down here. If we now replace that formula by the formula we had before, which is actually this one, then we can extend the DGS diagram to smaller ones. Now, for those who know DGS diagrams, what does that mean? Usually we have, if we double our indication size, we have a 12 dB difference between those two lines. That's true for big indications. But for small indications, it's not 12 dBs of difference, it's now 18 dB. So in the upper section, we have 12. And below 1/4 of the wavelength, we have to space them by 18 dB. So, summary. It was a long video, or it is a long video. And I'm glad you watched all the way to this point. and that you will watch it all the way to the end. Now what we know by now is that we have a lower limit for both DAC and DGS, which is a quarter of the wavelength. So until a quarter of the wavelength, you can trust those methods. If you go smaller, there are big question marks to its accuracy. But with DGS, we can actually extend DGS to going way smaller. So if you want to use those methods for something that small, this is perhaps where you want to use the extended DGS method. So, thanks a lot for watching this video. I think it is the longest video I produced up to the moment. If you have any comments, if you have any questions, feel free to write them down here in the comment section. And next time, let's see. I think I want to do some video where I combine those two things I have on this channel, the UT and the NDE 4.0, to get into use cases for UT 4.0. As usual, you will find more information in the description. I hope you like this video. I hope you subscribe to this channel. I hope I will see you soon. So thank you for watching. Thank you for giving a thumbs up. See you soon. Thank you and bye.